Hello everyone, welcome back to the channel. In today's video, we're diving into an essential topic for Python interviews: memory management. Python is well known for handling memory automatically with features like garbage collection and reference counting. But understanding how memory management works under the hood is crucial when optimizing your code and preparing for technical interviews. Today, we'll explore practical questions that can help you understand memory efficiency, avoid memory leaks, and optimize resource usage. By the end of this video, you'll have a clear understanding of how to manage memory in Python and how to answer those tricky memory related interview questions. Definition: memory management in Python is largely automated thanks to a combination of reference counting and garbage collection. Python keeps track of how many references point to an object, and when that reference count drops to zero, meaning no variables are using the object, the memory it occupies is automatically freed up. On top of that, Python's garbage collector steps in to handle more complex cases like circular references where reference counting alone would fail. Understanding memory management techniques like using weakref to create weak references or employing underscore underscore slots underscore underscore to reduce memory overhead in class instances can be crucial for developers. These tools help optimize memory usage, prevent memory leaks, and ensure your Python applications run smoothly, especially in long running systems. Let's check out some of the most frequently asked practical interview questions in Python. These examples will help you gain a deeper understanding of key concepts and prepare you to tackle them confidently in your next coding interview. 1. Reference counting. Question: write code to create an object and check how many references are pointing to it. Then create more references and delete them, observing the changes in the reference count. In this example, we explore how Python's reference counting works using the sys.getRefCount function. We start by creating a list of 1, 2, 3, and immediately check the reference count of the object using sys.getRefCount A. This function returns the number of references to the object, which includes not only but also the reference created within the getRefCount function call itself. Next, we create two additional references, B and CA, pointing to the same list object. As a result, the reference count increases, which we confirm by printing the updated count. Every time a new variable points to the same object, the reference count increases. We then delete one of the references, del B, which reduces the reference count. Even after deleting B, both A and C still point to the list, so the object remains in memory. Finally, when we delete both A and C using del A and del C, there are no remaining references to the object. At this point, Python's memory management system automatically deallocates the memory used by the list since no variable is referencing it anymore. 2. Garbage collection. Question: write code to demonstrate Python's garbage collection by creating two objects that reference each other. Then manually trigger garbage collection after removing the references. This code demonstrates how Python handles circular references and utilizes the garbage collection module to clean up memory when objects are no longer needed. The code begins by importing the GIS module, which allows us to manually manage the garbage collection process. A class node is then defined, where each instance has an attribute value and an attribute ref, which can hold a reference to another node. Two instances of the node class, node 1 and node 2, are created with values 1 and 2 respectively. After their creation, circular references are established. Node 1 references node 2 via its ref attribute, and node 2 references node 1. This creates a circular reference where each object points to the other, making it impossible for Python's default reference counting mechanism to detect that they are no longer needed. To address this, the garbage collection mechanism is triggered manually by calling gc.collect. This function forces Python to check for unreachable objects, including those caught in circular references, and cleans them up. Next, the references to node 1 and node 2 are explicitly deleted using the del statement. However, even after deletion, the circular reference still exists in memory until the garbage collector runs again to break the cycle and free the objects. Finally, after calling gc.collect a second time, the number of objects freed by the garbage collector is printed. This process ensures that the memory occupied by node 1 and node 2 is properly reclaimed, preventing memory leaks due to circular references. This code effectively demonstrates how Python's garbage collector helps manage memory in scenarios where reference counting alone cannot break circular dependencies between objects. 3. Checking object memory usage. Question: write code to check the memory size of different Python objects: integer, list, and using sys.getSysOS. In this example, we use the sys.getSysOf function to determine the memory size in bytes of different Python objects: an integer, a list, and a string. Each object in Python consumes memory based on its type and the values it holds. By calling size.getSizeOf, we can see how much memory each object occupies in memory. The integer x, which holds the value 10, takes up 28 bytes. In Python, even simple integers have a certain amount of overhead, which includes metadata like the object's reference count and type information. This is why an integer consumes more memory than just the raw binary representation of the number. The list y, which contains three integers 1, 2, 3, takes up 88 bytes. This memory size represents the list structure itself, not the actual memory used by the elements. Python lists are dynamic arrays, meaning they allocate additional space for future elements. So the 88 bytes include some overhead for list management and the flexibility to grow. The strings A, which holds the text Python, takes up 55 bytes. Strings in Python are immutable and come with extra metadata for storing things like the length of the string, its encoding, and reference counts. Even though Python is a short string, the total memory usage reflects the overhead of managing strings in Python. 4. Avoiding memory leaks with circular references. Question: write code to demonstrate how circular references can cause memory leaks and use garbage collection to avoid it. In this code, we define a class called leaky class, which demonstrates how circular references can potentially lead to memory leaks in Python. The class has an initializer underscore underscore init underscore underscore that takes a value and assigns it to an instance attribute, which serves as an identifier for the object. Additionally, the class has a destructor underscore underscore del underscore 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 that prints a message when the object is deleted, giving us a visual confirmation of when the object is removed from memory. Two instances of leaky class are created, A and B. Object I is assigned a reference to object B through its other attribute and vice versa. This creates a circular reference between the two objects, meaning that each object keeps the other alive in memory by holding a reference to it. Under normal circumstances, Python uses reference counting to manage memory. But reference counting alone cannot handle circular references because each object in the cycle has at least one reference keeping it from being freed. To deal with the potential memory leak caused by this circular reference, we manually delete the references to A and B using the del keyword. However, simply deleting these references does not immediately free the objects from memory as the circular references still exist. Therefore, we call gc.collect, which manually triggers Python's garbage collector. The garbage collector is responsible for identifying and cleaning up unreachable objects, including those caught in circular references, ensuring that memory is properly freed. After calling gc.collect, the destructor underscore underscore del underscore underscore is called for both objects, and the message confirming their deletion is printed. This example highlights the importance of understanding memory management in Python, particularly when dealing with circular references, which can prevent memory from being automatically freed unless the garbage collector is explicitly invoked. 5. Using weak references. Question: write code to avoid memory leaks by using weakref, which allows objects to be referenced without increasing the reference count. In this code, we explore the concept of weak references in Python, which allow an object to be referenced without preventing it from being garbage collected when all strong references are removed. First, a class myClass is defined with an initializer that assigns a name to each object and a destructor underscore underscore del underscore underscore that prints a message when the object is deleted, helping to confirm when the object is removed from memory. A strong reference to an instance of myClass is created and assigned to the variable object, ensuring that the object remains in memory as long as this reference exists. Next, a weak reference to the same object is created using weakref.refObj. Unlike strong references, weak references do not increase the reference count of the object, meaning they allow the object to be garbage collected when no strong references remain. The object can still be accessed through the weak reference as shown by printing weak underscore ref.name. When the strong reference object is deleted using del object, the object is now eligible for garbage collection since the weak reference alone does not keep it alive. After running the garbage collector manually with g.collect, the object is removed from memory and the destructor message confirms its deletion. This example highlights how weak references can be used to reference an object without preventing it from being garbage collected, making them useful in situations like catching or resource management, where you don't want to unintentionally keep objects alive. 6. Memory optimization with underscore underscore slots underscore underscore. Question write code that demonstrates how using underscore underscore slots underscore 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 in class definitions can optimize memory usage by restricting dynamic attribute creation. This code demonstrates the difference between a regular Python class and a class that uses the underscore underscore slots underscore underscore attribute in terms of memory efficiency. In Python, when you create a class by default, instances of that class can have any number of attributes added to them dynamically. This flexibility comes with a cost in terms of memory because Python uses a built-in structure called the dictionary underscore underscore dict underscore um, underscore to storage instances attributes which consumes extra memory. Regular class, the first class regular class is a typical Python class where each instance stores its attributes x and y in a dictionary underscore underscore dict underscore addix underscore. This allows new attributes to be added dynamically, but it also results in higher memory usage due to the overhead of maintaining a dictionary for each instance. Slot class, the second class, slot class uses the underscore underscore slots underscore underscore attribute to limit the instance attributes to only x and ei. By defining underscore underscore as underscore underscore underscore, Python no longer needs to allocate memory for the underscore underscore addict underscore 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 for each instance, which significantly reduces memory usage. This is particularly useful when creating many instances of a class as the memory savings can add up. However, it also means that you cannot dynamically add new attributes to instances of this class. Memory comparison. After creating instances of both regular class and slot class, we compare their memory usage using sys.getSizeOf. This function gives the memory size in bytes for each object. The instance of slot class will generally have a smaller memory footprint compared to the instance of regular class because the underscore underscore slots underscore underscore mechanism avoids the overhead of using a dictionary to store instance attributes. By running the code, you will see that the object created from slot class uses less memory than the one from regular class, highlighting how underscore underscore slots underscore underscore can be an effective optimization for reducing memory usage, especially in scenarios where you are creating many instances of the class. The current memory sizes for both objects are the same 48 bytes because we are working with a small number of attributes. But the difference will become more significant when dealing with a large dataset or creating many instances. 7. Memory profiling with tracemalloc. Question: explain what tracemalloc is and why it is useful for memory management in Python. This code demonstrates how to track memory allocations in Python using the tracemalloc module. The module is used to monitor memory usage during the execution of the program, allowing developers to identify how much memory is being consumed by different operations. In this example, the create underscore data function generates a list containing 1 million integers, which requires a significant amount of memory. The process starts by calling tracemalloc.start, which enables memory allocation tracking. After that, the create underscore data function is executed, creating the large list and storing it in the data variable. Following this, tracemalloc.get underscore traced underscore memory is used to retrieve two key metrics, the current memory usage and the peak memory usage. These values are then converted from bytes to megabytes and printed out for easier interpretation. The current memory usage represents the amount of memory being used by the program at the moment of the call, while the peak memory usage indicates the maximum amount of memory that was used at any point during execution. Finally, tracemalloc.stop is called to stop the memory tracking process and free the resources used by the module. This code is useful for understanding how much memory is consumed by the creation of large data structures like lists, and it can help optimize memory usage in applications. 8. Optimizing memory with array module. Question: what is the array module in Python and how does it help in optimizing memory usage compared to lists? This code compares the memory usage of a Python list and a Python array to highlight the memory efficiency of arrays. when dealing with large amounts of homogeneous data. The code begins by importing two modules, size, which provides the basis of function to calculate the memory size of an object, and array from the Python array module, which enables the creation of memory efficient arrays. First, a list named list underscore nums is created using a list comprehension that generates integers from 0 to 990. Lists in Python are versatile and can store different types of data, but they also incur memory overhead because each element is stored as a separate Python object. In addition, lists dynamically resize to accommodate more elements, leading to further memory overhead. Next, an array named array underscore nums is created from the list underscore nums using the itype code, which specifies that the array will store signed integers. Unlike lists, arrays store data in a contiguous block of memory, similar to how arrays are stored in languages like C. This makes them more memory efficient because there is no need to store the extra information that Python lists require, such as object references and metadata. The sys.getSys function is then used to measure and print the memory size of both the list and the array. Since the list stores each integer as a full Python object, it typically consumes more memory than the array, which stores the integers in a compact binary format. As a result, arrays are particularly useful for applications where large amounts of numeric data need to be stored efficiently, making them a better choice than lists in scenarios that prioritize memory optimization. That wraps up today's video on memory management in Python. We've covered some key concepts including reference counting, garbage collection, and avoiding memory leaks. Understanding how memory works behind the scenes is crucial not just for interviews but also for writing efficient high performance code. If you found this video helpful, make sure to give it a thumbs up and don't forget to subscribe for more Python interview prep and coding tips. Drop any questions you have in the comments and let me know what topics you'd like me to cover next. Thanks for watching and I'll see you in the next one.